Now we want to start talking about applications of derivatives, mainly as they relate to what we call maximums and minimums. And so this is really determinant on the behavior of the graph and seeing what happens with the graph as we move along. When I say the word maximum or minimum, I believe everyone would understand what I'm saying. As far as on the graph of a function, we're talking about a maximum point or a minimum point, and we're asking the question, can we find one? Do we have one? We're also going to talk about something called increasing and decreasing, which should be familiar terms to you. You should have seen that or heard of those when you're in pre-calc. And so we have this definition of what we call extrema. And extrema are, in fact, these maximums and minimum values. So we would say that f of c is a minimum of some function on an interval I if f of c is less than f of x for all x and I. What does that mean? Well, you think about it. If I was to draw a curve and I look at this point right here, on this interval around this point, this y value, f of c, which would be the y value for this particular c value, the y value here is less than all the other y values around it. So when I look to the left and when I look to the right, all the y values on either side are greater than. F of x for all other x's is bigger than this particular one, which would create a minimum. Conversely, f of c, f of c is a maximum of f on I if f of c is greater than f of x for all x and I. So we look at this point. And in this point, if we look at all the points around it, some random interval around it, you look to the left, you look to the right, all the y values, the f of x values around it are smaller than this particular y value, f of c, making this one the maximum. And so this is no different than probably what you would have already known about maximum or minimum without me giving you any type of definition. Now we can talk about absolute minimums and maximums, or we can talk about what we call relative or also local minimums and maximums. And that's really determining whether or not we're talking about an area or an interval on the graph or the entire graph itself. And so are we talking about the highest point overall or just the highest point in this particular location? And that would be absolute versus relative. Now sometimes if you have a function that looks like this being a maximum point, while it is a local or relative maximum in this area, it is also the absolute maximum for the entire graph. So, the difference between relative and absolute, there is a difference, but sometimes you can be both. Here is another curve. And in looking at this curve here, we see that we have these 3 points. This point, this point, and this point. Each one of these is a relative or local extrema, in which case this is a local minimum point, this is a local maximum point, and this is a local minimum point. Now, in looking at these in terms of absolute, none of these are the absolute maximum point. If you think about this graph that infinitely goes up this way and infinitely goes up this way, it wouldn't have a maximum, an absolute maximum, but it does have this local maximum. Okay? As far as minimums go, while these both are relative minimums, this minimum has a lower y value than this minimum does, and this y value is the lowest y value of any y value on this entire function. Therefore, this y value for this point would be what we consider the absolute minimum. So in comparison, when looking at all these, this is a local max and only a local max. This is a local min and only a local min. And this one is a local min, but also an absolute minimum. Now, sometimes that doesn't necessarily matter a whole lot. Sometimes we're just looking for the minimum or maximum in the graph in general. One thing that you see that sticks out with these 3 points are they're what we called in pre-calc turning points. It's where the graph turns from going downward to going upward, which we also describe as increasing and decreasing. We'll talk about that in a few minutes. So these points have some significance to them. So what we're going to do is we're going to try and find these local maximums and minimums. And once we find the local maximum and minimums, we know that some of them may in fact be absolute maximums or minimums. But really, we look at local or relative. So here's a question. Think about this function here. This function has relative extrema at both this point 0, 0 and this point 2, -4. Look at the relationship between the derivative of this function and these points in the derivative. And that's going to lead us to a method for looking for these turning points. And so the derivative of f of x is very easy to find, 3x squared minus 6x. If we look at this at 0, 0, we find f prime of 0, in which case we get 3 times 0 squared minus 6 times 0, and we end up with 0. If we look at this at 2, -4, we find f prime of 2, in which case we get 3 times 2 squared minus 6 times 2, which also gives us 0. And this is no coincidence. The fact that this point and this point are relative extrema, now we don't know whether they're maximums or minimums, but this question says these are relative extrema. And seeing that the derivative ends up being 0 in both cases is going to lead us into figuring out how to find these local max and mins. It's a little more involved than that, but that's the start. So that brings us to this definition of a critical number, or what we also call a critical value. So looking at this definition of a critical number, it says, let some function f be defined at C. So that means the function exists at C. You can plug C into the function. It says if the derivative at C equals 0, or if f is not differentiable at C, which means the derivative does not exist, then C is what we call a critical number. So in defining a critical number is any place where the derivative of a function is either 0 or does not exist. Okay. Then we have this theorem, which we call Fermat's theorem. Name of the theorem not as important as the theorem itself. It talks about the idea of relative extrema and critical numbers. And it says if f is to have a relative minimum or maximum at a particular location x equals c, then c is a critical number of f. Now, this is an if-then statement. We've talked about this previously. These can only be read in one direction. If we are going to have a minimum or maximum, it would have to occur at a critical number. What it doesn't say is that if we have a critical number, then we automatically have a maximum or minimum. That's not what it says, because not every critical number will in fact be a max or min. But the only place we could possibly have a max or min would be at critical numbers. So that's what you need to understand from this theorem. So looking at these graphs here, clearly we have a minimum, maximum, minimum here. And just so happens that if you look at the slope or the tangent lines here, you would get a slope of 0, which would create a horizontal tangent line. Now that should make a little bit of sense to you in that if you think about when we go this way, we're decreasing, then we're increasing. What you know about slopes and lines, if you have a line that goes down from left to right, the slope is negative. And if the line goes up from left to right, the slope is positive. Well, if we're going from negative to positive, you would think, well, maybe we stop through 0 to get there. Positive to negative. And this is all going to come into play in a couple minutes. But you could just think of, what would the tangent line look here? The tangent line would look like a horizontal line, and the slope right here would be 0, which means the derivative is 0. But that's not the only place where you could have a max or a min. Look at this point right here. This point right here is a minimum in this graph. These are two maximums, but we're not looking at those points right now. This point right here. This point right here, being a minimum, does not have the derivative to be 0 because it's a sharp point. We talked about sharp points. The derivative won't exist at a sharp point. The function's not differentiable there. It's continuous but not differentiable. So we also need to know this to be able to find critical points. Now again, not every critical point will be a max or min. We talked about graphs that look like this. We talked about this point right here, where the tangent line essentially goes vertical. If the tangent line goes vertical, the slope, or the derivative, does not exist. The function exists, the derivative doesn't exist, and this is in no way a max or a min, it's just a point on the graph. And so, just because the derivative doesn't exist does not necessarily mean that we have a max or min. Okay. So let's start by answering this question. Find the critical numbers for f of x. If you can't find the critical numbers, really can't go any further. So we need to be able to find the critical numbers. How do we do that? We first find the derivative. Should be a pretty easy question to answer here. The derivative would be 6x squared plus 6x minus 12. And so what I need for critical numbers is to find when the derivative equals 0 and when the derivative does not exist. Well, this is my derivative. It is a polynomial, specifically a quadratic polynomial, but a polynomial. As far as asking when does this polynomial not exist, the answer is, well, never. I mean, this function exists all the time. It's continuous everywhere. Its domain is all real numbers. So this is not something that would come into play for this particular problem. But it could equal 0. So how do I figure out when this quadratic will equal 0? Well, I got to solve the quadratic equation. You should be 100% capable of solving quadratic equations. You should know how to solve it by factoring. You should know how to solve it by quadratic formula. You should know how to solve it by completing the square. You should know how to solve it if you need extracting the roots. Not all methods will work for every quadratic, but you should be able to do every single method without any issue. In this case, they always try to do factoring first. I'll factor out a 6. I'm left with x squared plus x minus 2. If I can factor it more, I will, which would be x plus 2, x minus 1. And now I see that this will equal 0 when x equals negative 2 or when x equals 1. So therefore, there are two critical numbers for this function, which tells me that there are two places that I could possibly have relative extrema. And these are the only two places that I could have relative extrema. But not saying that both of them are relative extrema. But it's the only two places where this function could possibly have relative extrema. So now the question is, all right, how do we determine if this is a relative extrema and what kind? Is it a max or a min? Same thing with this one. In order to answer that question, we need to first talk about the concept of increasing and decreasing functions. This should be nothing new. You should be familiar with the concept of increasing and decreasing. The definition of an increasing function is that we say a function f is increasing on some interval if for any two x1s and x2s in that interval where x1 is less than x2, f of x1 is also less than f of x2. you should know that increasing means going up from left to right. Well, if I'm going up from left to right and I think of 2 points on that graph, here's one x value, here's the other x value, so x1 and x2. x1 is clearly less than x2 because it's to the left. Now look at the corresponding y values. The y value here, which would be f of x1, and the y value here, which is f of x2. F of x2 is bigger. x1 is smaller, f of x1 is smaller than x2 and f of x2 corresponding. And that happens because simply the graph is moving upward from left to right. If we have the definition for decreasing, also very simple. A function is decreasing on an interval for any two x1s and x2s on that interval. If x1 is less than x2, implies that f of x1 is now bigger than f of x2. Same thing, just in reverse. We flip the x's and y's, flip the y's, but the x's stay the same. Here's your 2 points. Now, if this is x1 and this is x2, still set up where x1 is less than x2. Look at the corresponding y's. Now f of x1 is bigger than f of x2. So you know these definitions. These should not be anything new, but we're going to use this concept of increasing and decreasing to answer the ultimate question of max and mins. So if we want to test to find where a function is increasing and decreasing, we do it by looking at the derivative. The derivative represents the slope. You learned back in algebra that if you have a line that goes up from left to right, the slope is positive. And if the line goes down from left to right, the slope is negative. And if it goes horizontal, the slope is 0. Well, that's for lines, but that goes for any graph. If you graph any function, the same thing should happen. So if my function is going down from left to right, which you see is happening right here, the derivative over that entire stretch of the graph should be negative, should be less than 0. Here, my graph is going up from left to right. So over that entire interval, for every value in that interval, if I look at the derivative of this function, the derivative will always be positive, greater than 0. And for this stretch of this function, since it goes horizontal, the derivative would be 0. Another way to look at it is in terms of the tangent lines. We could just think straight in terms of lines. If you think about the tangent line to the graph here and here, those lines are going up from left to right. So those lines have a positive slope, but the tangent line has the same slope as the function does at each of these locations. So if the tangent line slope is positive, the function slope is positive. And the same thing could be said for these. So if a derivative is positive, then the function is increasing. If a derivative is negative, then the function is decreasing. And if the derivative for some function is 0, then we say the function is constant. So what we want to do is find where is the function increasing and decreasing. Where is the derivative positive or negative? So this is how we're going to do it. First, we're going to locate the critical numbers. Those are the places where the derivative is 0 and undefined. Then from there, we will determine the sign of the derivative by using some test values. Okay? Once we determine the sign of the derivative, we'll use that sign of the derivative, positive or negative, to determine where the function is increasing, decreasing, and or constant. And we'll represent those in interval notation. Okay? Why are we doing this? Why does this work? Well, it's based off of something that you would have seen in algebra or pre-calculus when you were solving inequalities, and that's ultimately what we're doing. If we're trying to figure out where something is greater than 0 or something less than 0, when I say something, I mean the function's derivative, you're solving an inequality. And when you solved inequalities, you looked at this idea of any function can take on one of 4 possible values. It could be positive. When I take any function, specifically we're looking at the derivative function. If I look at this function, I plug something in, I could get a positive answer to come out. I can get a negative answer to come out.
I could get 0, and I could just get something that does not exist, or we also would say undefined, right? So if we find the critical numbers, we're finding what values we can plug into the function that would make this happen. Which means the only thing left is that when we plug something into the function, and I say function, I mean the derivative function, only thing left would be if we plug something into the derivative function that we get a positive or negative answer out. And that's ultimately what we're looking. Increasing, positive, decreasing, negative. So we're basically narrowing down this idea by finding this first, cutting these off, and then looking at these values. Again, something you would have done in pre-calc in solving polynomial or rational inequalities. So we have this question here that we're going to work out. And it says, so we want to find the open intervals on which this function is increasing and decreasing. So in order to do that, we're first going to say, let's find the critical numbers. In order to find the critical numbers, we need to know what the derivative looks like. So let's find the derivative. Should be pretty easy for this function. You see it is. We get 3x squared minus 3x. This power comes out, but it cancels with this 2, so we just get 3x. So in order to find the critical numbers, we need to find where the derivative equals 0 or where the derivative does not exist. Again, the derivative is a polynomial function. It exists everywhere, so we don't worry about this. That's not going to happen every time. We'll get some examples where we have to worry about it not existing. But it could equal 0. Where does it equal 0? Well, we got to solve this equation. Again, another quadratic. Factor out 3x, we get x minus 1. So we find out when x equals 0, when x equals 1 is where it equals 0. So it never does not exist, and it only equals 0 at 2 places. Which means any other x value, when I plug it into the derivative will either be positive or negative, because we've already crossed this and this off the list. So now what we're going to do is we're going to make this little chart. We're going to place these two critical numbers onto our chart as the number line. What it does is it divvies our number line up into 3 intervals. The interval from here to here, the interval from here to here, and here to here. So we're going from negative infinity to 0, 0 to 1, 1 to positive infinity. We're working with the derivative, so it's important to label this as such. You'll see why that's going to be important as we move forward. And what we need to do is say, if I take some value in this interval, let's say negative 1, and I plug it into the derivative, what kind of answer do I get? Now when I plug negative 1 into the derivative, what you see is that you end up getting a positive answer. Okay? That's simply found by just plugging it in and doing the computation. Now, what you would have learned in pre-calc would be this. Since I already cleared out where the function, derivative function, does not exist and equals 0, everywhere else it is either going to be positive or negative. Also, in this interval, if this one value makes the derivative function positive, then everything in this interval will make the derivative positive. Then I go to the next interval, which would be, say, pick any number. I'll pick a half. I plug that into my derivative, so I find f prime of a half, and I see what kind of answer I get. Now, I really don't care what the answer actually is. I just care what kind of answer I get. So the kind of answer that I get, positive or negative, is really what's important. So you see that when I plug a half in to the derivative, I'm going to get 3 times 1/4 minus 3 times a half, which is 3/4 minus 3/2. You should understand that this number is smaller than this number. A smaller number minus a bigger number would yield a negative. If 1/2 yields a negative, every x value between 0 and 1 would make the derivative negative. Finally, I'll plug in, say, 2. I'll find f prime of 2. That's going to give me a positive value. So this interval yields positives throughout. So now what does this tell us? What it tells us is that from negative infinity to 0, my derivative is positive, which means my function is increasing. Then from 0 to 1, my derivative is negative, so my function is decreasing. And then from 1 to infinity, my derivative is positive, so my function is increasing. So to answer this question, f of x is increasing on the interval from negative infinity to 0 and from 1 to infinity. We could also say that f of x is decreasing on the interval from 0 to 1. Now notice these are open intervals. I have parentheses, not closed intervals, which I would use brackets. That's simply because I don't want to include 0 or 1 in these intervals, because the derivative isn't positive at 0. The derivative is 0 at 0. The derivative isn't positive or negative at 1. The derivative is 0 at 1. When the derivative is 0, we're not increasing or decreasing, but yet we're constant. So this is the answer to this question. Notice I talk about the function increasing and the function decreasing. Everything we did in terms of the computation in here, we were working with the derivative, but this is all describing what's happening with the function itself. Okay. Next step would be to take this one step further, not necessarily what this question was asking for, but let's take it one step further. If my function is increasing, then decreasing, then increasing, what do you think's happening with this value where it switches, where x is 0? Well, if it's increasing and decreasing, it looks like that point may be a maximum point. And same thing here, but on the minimum side. I say looks like because it's not guaranteed to be a maximum or minimum. The question is, does this x value yield any result when I plug it into the function? Is there a point on this function where the x value is 0? Because if this point right here doesn't exist, how could it be a maximum? So if I switch from increasing to decreasing and this point exists, then I can say that that point is a maximum. If I switch from decreasing to increasing and this point exists, then I can say that that point's a minimum. Let me show you something. Here's a vertical asymptote. On one side of the vertical asymptote, my function is increasing. On the other side of the vertical asymptote, my function is decreasing, going up from left to right, going down from left to right. I am switching from going up to going down on either side of this value right here, c. But this value c does not yield a maximum point. There's no point at all. So that's the problem. If you just look at going up, switching to going down, and think you have a maximum, you could get into trouble. So everything we discussed brings us to this first derivative test. The first derivative test essentially sums up everything that we just got done saying. What it says is that if we look at a function and we find the critical numbers for that function, okay? Let's use something that you can actually see. There we go. And that function's continuous, which means it exists at c itself, okay? Then what we could say is if the derivative changes from negative to positive, so we go from decreasing to increasing, then that location will be a relative minimum as long as this point cf of c exists. If the derivative changes from positive to negative, then we'll have a relative maximum. And if it doesn't change at all, if it's positive on one side and positive on the other, or negative, then we have nothing. We don't have a maximum or a minimum. We just have a random point where the derivative just happened to be 0, or the derivative didn't exist. So here's 3 pictures. Look at this picture here. Look at this point right here. On this side of the point, my graph is increasing, my slope is positive. On this side of the point, my graph is decreasing, my slope is negative, and that yielded a maximum point. If we look at this one here, we look at this point. On this side, the graph is decreasing, then increasing, slope is negative, then slope is positive, and we yielded a minimum point. That doesn't always happen because look at this point right here. This point, the slope is 0. The derivative is 0. However, on this side, my slope is positive, and on this side, my slope is also positive. Yet, the tangent line right here is horizontal. The slope is 0. So just because you have a critical point, just because the slope is 0, the derivative is 0, doesn't mean it's always going to yield a max or min. It all depends on how the function behaves around that point. And if we're increasing and then increasing some more, we do not have a max or a min. We have neither. So we're going to look at this question to answer where are the relative extrema. All right, well, we need to find the derivative first. This should be pretty easy. 2/3 x squared minus 4 to the 1/3, or minus 1/3 I should say, times 2x. We use chain rule to get that answer. I'll rewrite this as 4x over 3 x squared minus 4 to the 1/3. This was negative x when it came down. The 2 and the 2x multiplied together gave me the 4x. The 3 was already in the denominator. And I'm going to say, okay, if this is my derivative, I want to find when is the derivative 0, when does the derivative not exist. Well, this being a fraction, both of these are possible. When would a fraction equal 0? Well, it'll equal 0 when the numerator equals 0. When would a fraction not exist? Well, that'll happen when the denominator equals 0. Well, these are both easy to solve. X would equal 0 would solve that. X equals plus and minus 2 would solve that. So we have 3 critical numbers. Now, next thing I want to do is I want to create a table that has these critical numbers laid out. That's my derivative table. It creates 4 separate intervals, and I'm going to test every single one. So I'll use, say, -3, I'll use -1, -1, +1, and +3. That's just a single value in each one of these intervals. I could have picked any value I want. These are fairly easy numbers to work with. And so what I'm going to do is I'm going to find f prime of -3. I'm going to find f prime of -1, f prime of 1, and f prime of 3, and see what kind of answer I get. Now again, the actual answer isn't as important as what kind of answer. So when I plug f and -3 into this derivative, I'm looking at what kind of answer I get. Well, if I plug -3 into the numerator, I'm going to get a negative answer. If I plug -3 into the denominator, well, this will be 9, minus 4 is 5, positive. 1/3 power is cube root of a positive is positive, times 3 is positive, so I get a positive. Well, overall, I got a negative in the top and a positive in the bottom, so that would yield a negative value overall. Again, I didn't look at the actual value, but I know that the answer will be negative. I do the same thing for -1 here and here, and I end up getting a positive. I plug +1 in here and here, I end up getting a negative. Plug 3 in here and here, I end up getting a positive. You can sit here and do the computation. You could plug 3 in, you could work it out. You can plug 1 in, work it out, and you'll see that this is what you get. Now, it just so happens I get something that alternates. Positive, negative, positive, negative. It started with a negative, but alternates back and forth. That's not always going to happen. Sometimes you'll get 2 positives in a row, positive and positive. Sometimes you get all positives straight across. Sometimes you get all negatives. You actually have to look at each interval individually and determine what kind of value you get. Now, what is this telling us? What it's telling us is that my function is decreasing, then increasing, then decreasing, then increasing. So then what does that tell me about the relative extrema? Well, it tells me that if this point in fact exists on the graph of this function, then this point will be a minimum. If this point, in fact, exists on the graph of this function, it will be a max, and same thing here, minimum. Well, how do I figure out if it exists on the graph of this function? Well, if I can find f of -2 and f of 0 and f of 2, then each one of these individually will exist. Well, what happens? If I plug -2 in here, this becomes 4. 4 minus 4 is 0. 0 to 2/3 gives me 0. Same thing would happen if I plug -2 in, I get 0. If I plug 0 in, I'm going to get -4 to the 2/3. And f of 0 will end up equaling what now? It'll be 16, the cube root of 16. Right? So you see that each one of these values exists. And so what we have is relative extrema. We have a minimum. So f of x has a relative minimum at -2 comma 0, because this is the y value for that x value, and over here, which would be 2, 0, x value, y value, and f of x has a relative maximum at 0 cube root of 16. That was this location right here. This is the y, this is the x. So in finding the relative extrema for a function, we can do that by finding the critical numbers, looking at those critical numbers relative to the derivative, creating intervals where we determine whether or not the derivative is positive or negative, using the idea of increasing and decreasing to determine the max and mins. And what we just did there is we applied the first derivative test. All right, so here we want to find the relative extrema for this example, in which case, first thing we want to do is find the derivative. So if we go to find the derivative, we're going to need to use the quotient rule. The derivative of the numerator, 4x cubed, times the denominator, minus the derivative of the denominator is 2x times the numerator, all over the denominator squared. We need to simplify that, multiply these in, collect like terms. I get 4x to the 5th minus 2x to the 5th minus 2x, all over x to the 4th. Bring those x to the 5th together, I get 2x to the 5th minus 2x, all over x to the 4th. So here's my derivative. I need to find where the derivative equals 0 and where the derivative doesn't exist. So since this is a fraction, it equals 0 when the numerator equals 0, and it doesn't exist when the denominator equals 0. Solve this, we have to pull out a 2x, we get x to the 4th minus 1 equals 0. That'll give us x equals 0, and x equals plus or minus 1. To solve this, we get x equals 0. 0 showed up here, 0 also showed up here. It's just a single critical number that happened to be in both locations, but we have three critical numbers. -1, 0, and +1. So that divvies our number line up into 4 intervals. We're going to check -2, let's say -0.5, +0.5, and 2 in the derivative. Now notice, the denominator is x to the 4th. Being x to the 4th, no matter what I plug in, that will always be positive. So the only thing that's going to make the whole derivative positive or negative is really the numerator. So I got to look at what would happen if I plugged in -2, -0.5, 1/2, and 2 into the numerator. If it gets a negative, the whole thing's negative. If it gives me a positive, the whole thing's positive. So if I plug in -2 into the derivative and I find f prime of -2, this value here would be a fairly large negative number. This would be a fairly small positive number, specifically 4, so I'd get a negative. If I plug in -0.5, the reverse happens. This becomes smaller than this, okay? And so we get a positive. I plug in +0.5, okay? What's going to happen is this is going to be smaller, and we're going to get a negative, and then I would get a positive. You could simply take your time doing that, plug the value in, do the computation, find what the answer is. So then what we see is that our function is decreasing, then increasing, then decreasing, then increasing. Okay. Now the question is this right here a minimum? Is this a maximum? Is this a minimum? Well, that all depends on whether or not I can find f of -1 or f of 0 or f of +1. Now looking at these, f of -1 would be -1 to the 4th plus 1 over -1 squared. F of 1 would be 1 to the 4th plus 1 over 1 squared. Well, these would yield the same thing because of the even powers. I would get 2 over 1 in both cases, and I get 2. So these points exist. Now look at what happens when I plug in 0. 0 to the 4th plus 1 over 0 squared. Well, that gives me 1 over 0. Can't happen. This is undefined. Well, that tells me that this point doesn't exist. Therefore, this point can't be a maximum. But these do exist. So as far as the relative extrema go, I have f of x has a relative minimum at -1, 2 and +1, 2. And it has no relative maximums. Because the only critical number that could have possibly been a relative maximum, the function is undefined. Looking closer at this function and thinking about what that value really would be in the function, since only the denominator is 0 and not the numerator, that's going to be a vertical asymptote. So we're going to have this vertical asymptote when x equals 0. So my graph's going to do this or both up and down. But it's not going to have a maximal point there. What we can see is from this, since we're increasing on one side and decreasing on the other side, I can see that this is what's going to happen of my graph. If I have a vertical asymptote at 0, on one side I'm increasing, on the other side I'm decreasing. So right away I know the behavior of my graph around that vertical asymptote that's right here. But as far as the question goes, relative extrema, this is all we needed to know.